Hello everyone, welcome to this session on transformer architecture and BERT. In today's world, our daily life rely on NLP or natural language processing digitalized language functions like web search engine, emails, tweets, and many more. And in this session, we will look at the heart of all of that magic, transformer and BERT, how it internally works, how BERT uses transformer architecture, and so on. We will also look into a demo wherein we will fine-tune a BERT model to classify disaster tweets using Amazon SageMaker. I'm Suman Devnath, a Principal Developer Advocate from AWS India. If you have any questions about the content being discussed, please feel free to ask them. We'll be very happy to help you. Computers and machines are great at working with tabular and structural data, as we all know. But much of the information human generates has complex structure and definitely not tabular, making it very hard for computers to interpret. In NLP, the goal is to make computer understand this complex language structure and retrieve meaningful information from it, so that it can solve some complex problems like text classification, speech recognition, and so on. If we look at the history of NLP, we already know many popular word vector models like word2vec, GLOVE, and fast text. But the major breakthrough happened in last couple of years. In December 2017, a paper got released called Attention is All You Need, which changed the whole dynamics of NLP. And hence, the transformer was born. The transformer outperformed the existing state-of-the-art models and became a key component of NLP. And since then, we got many new NLP models which are based on transformer architecture, such as BERT, GPT, and T5. But before we dive into BERT, it is important for us to understand what is a transformer and how it internally works. Let's take an example of a language translation task of converting a sentence from English to French. The transformer consists of an encoder and a decoder architecture. We feed the input sentence, that is the English sentence in this example, to the encoder. The encoder learns the representation of the input sentence and sends the representation to the decoder. And the decoder then generates the output sentence, which is nothing but the target French sentence. But what's going on inside this encoder and the decoder block? Let's try to find out. The transformer consists of a stack of n number of encoders. Each encoder sends its output to the encoder above it. And the final encoder returns a better representation of the given input sentence. In the transformer paper, the author have used n equal to 6, meaning they have stacked 6 encoder blocks one after another. But how exactly this encoder block works? How it generates a better representation of the input sentence? For the sake of simplicity, let's consider n equal to 2. That is, we have 2 encoder blocks. All the encoder blocks are identical, and each encoder block consists of 2 sublayers. First, multi-head attention, and second, feed-forward network. We will now look into the details of these 2 sublayers, but before we see how multi-head attention works, we first need to understand what is self-attention mechanism, which is the core of transformer. Consider this following sentence. A dog ate the food because it was hungry. By reading this sentence, we can easily understand that the pronoun it implies to the dog and not to food. But how does our model understand this? This is where self-attention mechanism helps us. Because of self-attention, while computing the representation of each word, it relates each word to all other words in the sentence to understand more about that particular word. But how exactly does this work? Suppose our input sentence or the source sentence is I am good. First, we get the embedding of each word in the sentence, as we can see here. Note that embeddings are just the vector representation of the word, and the value of these embeddings will be learned during the training process. Let's assume the embedding dimension is 512. Then our input matrix X will have a dimension of 3 cross 512 as we have 3 words in the sentence. Now, from the input matrix X, we create 3 new matrices, namely a query matrix, a key matrix, and a value matrix. To create these 3 matrices, we introduce 3 new weight matrices called WQ, WK, and WV. We create these matrices by simply multiplying the input matrix by these 3 weight matrices respectively. So now, if we look at the first row of all of these 3 matrices, it would simply implies the query, key, and the value vector for the word I. But still, the ultimate question is why we are computing this. How is this going to help us? These are the 3 matrices which are used in the self-attention mechanism, which is nothing but a simple 4-step process. In the first step, we compute the dot product between the query matrix Q and the key matrix K, as we can see here. Computing the dot product between 2 vectors tells us the similarity between these 2 vectors. In step 2, we divide the resultant matrix by the square root of the dimension of the key vector. This is useful in obtaining a stable gradient. Now, if we look at the similarity score, we can understand that they are not at all normalized. So in step 3, we normalize them using a softmax function. So if you look at the first row of the score matrix now, it tells us that the word I is related to itself by 90%, to the word am by 7%, and to the word good by 3%. And finally, we compute the attention matrix Z by multiplying the score matrix with the value matrix. As you can see here, the attention matrix Z contains the attention value of each word in the sentence. But instead of having a single attention head, we can always create a multi-attention head, namely Z1, Z2, and so on. And this is going to be very useful in circumstances where the meaning of the actual word is ambiguous in the sentence. Like in this example, the word it is ambiguous, as it may refer to a dog or to food. One important thing to consider in transformer network is that we don't follow recurrence mechanism. Unlike RNNs, where we feed the sentence word by word, we feed all the words in the sentence parallelly to the transformer network. But the problem is how it will understand the meaning of the sentence if the word order is not retained. And this is where positional encoding helps. With positional encoding, we give some information about the word order to the transformer so that it can understand each word's position in the sentence. As you can see here, the dimension of the positional encoding matrix P is same as the dimension of the input matrix X. We simply add the positional encoding matrix to the embedding matrix and then feed that as an input to the network. But how it generates this positional encoding matrix? The author of the transformer used the sinusoidal function for computing the positional encoding. For example, assume that we have only 4 dimensions. So we generate 2 sine and 2 cosine functions of different frequencies. As you can see here in the example, the positional embedding of the 30th word is -1, -0.25, 0.91 and -0.25, which are nothing but the amplitude of those 4 functions. Let's recall from where we started. In our encoder block, the last thing that remains is the feed-forward network. The feed-forward network consists of 2 dense layers with ReLU activation. The parameter of the feed-forward network are same over different positions of the sentence and are different over the encoder blocks. One more important component in our encoder is the add and norm component. it connects the input and the output of a sublayer. As we can see here in the figure, in the form of dotted lines, the add and norm components is basically a residual connection followed by layer normalization. Layer normalization promotes faster training by preventing the value in each layer from changing heavily. Let's put all of them together and see how the whole encoder looks like. Here, the stack shows 2 encoder and only encoder 1 is expanded. We can stack n number of encoders one above another, and the output, that is the encoder representation obtained from the final encoder, that is the topmost encoder, will be the representation of the given input sentence. The decoder takes the encoder representation as the input and tries to generate the target sentence. In this example, the decoder will take the final representation of the English sentence "I am good" from the final layer of the encoder block, and it will be used as the input to generate the French sentence or the target sentence as output. Similar to the encoder block, we use n number of blocks for the decoder. We will not go into the details of the decoder block, but it's quite similar to the encoder block with subtle difference. Like, the decoder receives 2 inputs, one from the previous decoder and the other one is the encoder representation. The decoder block contains 3 sublayers: masked multi-head attention, and feed-forward neural network. If you wish to learn more about that, you may like to refer to the original paper of Transformer. Now that we have looked a bit about the internals of Transformer, it's time to switch gear and look into BERT, one of the most popular state-of-the-art text embedding models we have today. BERT stands for Bidirectional Encoder Representation from Transformer. It is taken directly from Transformer, but unlike Transformer, which consists of an encoder as well as a decoder block, in BERT we have only the encoder block. Let's take this sentence: Python is my favorite programming language. Here, BERT relates each word in the sentence to all other words in the sentence to understand the contextual meaning of every word. Unlike context-free models such as word2vec, which generates static embedding irrespective of the context. BERT is a pre-trained model. What is a pre-trained model? Say we have a model M. First, we train the model with a huge data set for a particular task and save the trained model. Now, for a new task, instead of initializing the new model with all random weights, we initialize the model with the weights of our already trained model M. The BERT model is pre-trained on a huge corpus for 2 interesting tasks called Masked Language Modeling or MLM and Next Sentence Prediction or NSP. BERT was trained to perform these 2 tasks purely as a way to force it to develop a sophisticated understanding of the language so that it can be fine-tuned later on for any other task, such as question answering, sentiment analysis, and so on. Let's take 2 sentences. Kolkata is a beautiful city. I love Kolkata. During the pre-training phase, BERT is supposed to predict the crossed out word, that is city, as a part of MLM, and as a part of NSP, it is supposed to predict if sentence B is found immediately after sentence A. Researchers of BERT have presented the model with different configurations, like BERT base and BERT large. Let's consider BERT base, which consists of 12 encoder layers. Let's see how it works. First, we have the token embedding layer, wherein we tokenize both the sentence and obtain the tokens. We add a new token called the CLS token at the beginning of the first sentence, and then we add new token called SEP at the end of every sentence. Next, we have the segment embedding layer. Segment embedding is used to distinguish between two given sentences. That is, if the first token belongs to sentence A, then the token will be mapped to an embedding EA, and if the token belongs to sentence B, then it will be mapped to an embedding of EB. At last, we have the positional embedding layer, which we have just learned a while back, that helps to provide information about the word order. And finally, we sum all the embedding together and feed them as an input to BERT, and it returns a representation of each token as an output. In the output, RCLS denotes the representation of the token CLS, and R Kolkata denotes the representation of token Kolkata. Like this, we have the representation of the other words as we can see here. And now we can use this representation and can fine-tune to solve a particular task. Let's take some example. Consider we have a task of sentiment analysis, which is nothing but a binary classification task, as the sentiment can be either positive or negative. Let's feed this sentence, Suman loves Kolkata, to BERT. Since it is a classification task, we simply take the representation of the CLS token and feed it to the feedforward network with a softmax function, which then returns the probability of our sentence to have a positive or a negative sentiment. But you may ask why we need to take the embedding of the CLS token alone. Why not the embedding of other tokens? The CLS token basically holds the aggregated representation of all the tokens. Thus, we can ignore the representation of all other tokens and simply take the representation of the CLS token called RCLS and feed it to the feedforward layer with a softmax function which returns the probability. Similarly, for any other task like name entity recognition, we can use the BERT pre-trained model and fine-tune it with a classifier. Then, the classifier can return the category of the name entity belongs to. Just like this, we can fine-tune the pre-trained BERT model for several downstream tasks. Now, let's jump into a demo wherein we will be using Amazon SageMaker and Transformer package from Hugging Face to fine-tune a BERT model for disaster tweet analysis.
All right, so let's jump into this demo. So we are going to use a Jupyter notebook for this particular demo. If you are new to SageMaker, what you can do is once you log into your AWS account, you can search for SageMaker and you will come up to this, on this homepage. And if you see on the left-hand side, you will have notebooks. And here, if you come to notebook instances, you can create a Jupyter notebook instance. Okay, and you can provide all the necessary information like what type of instance you want to host your Jupyter notebook and so on. And I've already created a notebook of instance type M5 to X large, and I've just opened this in another tab. So here, all this code will be available to you, and you might have seen the GitHub location for that in the presentation section. Feel free to pick up the code and play around with that. Okay, so now we are going to open this particular Jupyter notebook, and we are going to write the code to make a BERT model, or rather fine-tune a BERT model for disaster tweet classification. Now, if you want to know more about this problem, feel free to go over this URL, which is provided in this notebook. But the idea is, in today's world, we see a lot of disaster around us, and the first thing that we do is after calling the emergency services or the personnel who can help us in those situations, is we tweet that so that the right people or people get aware of the problem and they can come to that particular location and help out. Right, but if you look at it, there are a lot of agencies and companies who wish to have this information as soon as possible, right? And it is very difficult because of the language structure and because of the amount of information and tweets that the Twitter generates across the globe, it is very difficult to analyze that tweet by tweet. So we are going to write a model, or we are going to define a model which can analyze a particular tweet, and it can help us to understand whether that tweet is actually signifies a disaster or not. Now, the first thing is we need to install a transformer, and this is the package that we are going to use, which we get from the Hugging Face company. And you can always go over the Hugging Face website and have a look at their documentation. They have hundreds and thousands of pre-trained model which are based on transformers. Okay, and one heads up. Although we are going to use transformer separately and we are going to use transformer module, but just recently, a couple of weeks back, we introduced a collaboration between AWS and Hugging Face, wherein you can make use of Hugging Face libraries directly from SageMaker SDK, as you can see here. You don't have to install Transformer separately. You can always use the SageMaker SDK and import the Hugging Face library and make use of that. Okay, and we are going to use SageMaker anyway for our demo. But the point I'm trying to make is you should explore this new capability wherein you can make use of Transformer based pre-trained model which are offered by Hugging Face directly from SageMaker SDK. Okay, so let's go back to our notebook and see how we can proceed towards this problem. So first, we are importing few of these libraries, NumPy, Pandas, and SageMaker. So SageMaker is the SDK in Python, which you can use to make use of all the resources that SageMaker provides. So first thing is we are creating a session that provides all the methods in the SageMaker resources, and then we are defining the bucket name. This is an S3 bucket. So S3 is a simple storage service from AWS, which is an object-based storage service offered by AWS, wherein you can create a bucket and dump your data. Right. And we are also defining a prefix so that you don't have to keep on creating new buckets for all of your training. So you can always have a single bucket with different prefix so that it can help you to segregate your training job for different types of problems. So we are going to use this bucket and prefix at a later point in time, whenever we have to provide the location of our training data set or the model artifacts, to SageMaker. And we are going to see that in a while that how we are going to use this bucket to store our training and test data and also the model artifacts after the training process. Next, we are just defining the role because SageMaker need to talk to S3, right? So it should have the right execution role. And this is the role which we create at the time of creating the Jupyter Notebook instance. And in this line of code, what we are essentially doing is we are creating an object called role instance of the get execution role method, and we are going to use this role and pass it during the training process so that SageMaker can assume that role and access the necessary resources. Next, we are going to prepare the data set. So this is all the data is taken from this particular website, Kaggle website, because this was there was a I guess a couple of months back there was a Kaggle competition around this problem, and you can always go over this link and get much more details about the data set and the problem. I have already downloaded that and kept it inside this dataset folder. If you come here, there is the dataset folder. Inside that, I have this tweet dataset in the form of CSV file. Now, this particular dataset has lots of columns, but we are interested in only two columns, that is labels and sentences, where label indicates whether tweet is a disaster, contains a disastrous or not, and the column 3 contains the actual sentence, or rather the tweet. So we can have a look at the data frame. We are using pandas to load that data set. And if you can see this data set, there are a lot of information which we may not need. Like there are some hashtags, there are some URLs, and so on. Right, and it might so happen that we have emojis, right? Because in tweets we do use emojis a lot. Now, we need to clean this data before we feed that data to the BERT model, right? So we are not going to do an exhaustive cleaning, but just to give you an intuition of how you can do the cleaning of the data set, we use some helper function which can help you to clean the URLs, emojis, HTML tags, and so on, right? And we are just using a lambda function to all the data that we have on all the data that we have, and pass through all of these helper function so that we get a cleaner tweet, right? So now if you look at the tweets, it's pretty clean, right? And if you look at the same tweets starting from the 80th line to the 84th line, you will see that there is no URLs and no hashtags and so on. If you see, go up and see this, we use the same sentences or tweets before, but we had this URLs and hashtags and so on, right? So those we got rid of all of that, messages. All right. So now that we are done with a little bit of cleaning, we can do some analysis on our data set. So we are just want to make sure that our data set is rightly balanced, right? So what do we mean by balanced? We want to make sure that the number of tweets that we have in our data set has an equal number of or roughly equal number of distribution across two different classes. So as we can see, we have out of all the data set, which is roughly around 7,000 or 8,000 odd tweets, we have roughly around 57% of the tweets which are tagged as non-disaster, and there are roughly around 43% of the tweets which are real disaster. So it's kind of a quite a balanced data set, so we can go ahead with that. Although the number of data points is less, so we may not expect a very highly accurate model at the end of the day, but for the demo purpose, it's completely fine. So next, we can do some more analysis to understand, how many words we have in each of these tweets. So we are just plotting that in this chart, and you can see that most of the tweets are, ranging between 10 to 17 or 18 words. So which is quite understandable, right? So if you look at tweets, they are short, they are not that long. So this is important because at later point in time, we will see that there is a limit that we put in our code where we will say that the maximum size of the sentence. So this will give you an idea about the sentence length that you should set while you do the training. Okay, so now that we have analyzed the data, it's time to split the data for training and testing. So we can always do that manually, but we have a wonderful function or method called train test split from scikit-learn library. So we are just using that, and we are passing this data frame, and we are saving the data in train and test variables respectively. And after that, we are saving it into a CSV file. And ultimately, we need to push that data to Amazon S3. And this is where we are going to use the bucket and the prefix, which we have declared before. So essentially what we are doing is we did the analysis on this notebook. We downloaded the data set in our notebook. And now, after cleaning the data, and splitting the data between train and test, we are uploading the data to Amazon S3. And why we are doing this? Because in SageMaker, when we start the training, SageMaker training will not happen in this particular notebook, right? As we will see next. But if the training happens somewhere else, we need to make sure that the data is accessible to that SageMaker training instance, right? So that's why we are just pushing the data to Amazon S3. Now, this is a brief introduction to Amazon SageMaker if you are new to it. So when you start the training job, what essentially happens is SageMaker will read the data from Amazon S3 and make that data available into the model training instance, which is nothing but a container. And it creates a container on your behalf from a particular image, right? And that image could be anything. So based on your requirement. So in this code, we are going to use PyTorch. So we will specify a PyTorch estimator. But if you write a code in TensorFlow or MXNet, you can make use of the right container, right? And Amazon will fetch that container from a repository called Amazon Elastic Container Registry. So you can think of ECR as an repository where all the container images are there. right? So it will take that image, it will create a container, and that container will be used during your training process. And that container will have the access to the S3 bucket where you will be keeping your training and test data set. Okay, and once the training is over, it will just destroy that instance so that you are just built for the time the training is done. Okay, so similarly, once the training is over, at the time of deployment, you again have to define what type of container you want and where exactly the dataset or the model artifacts resides, and it will create an instance of uh, of a container. Which will be used for your endpoint, and we are going to see that in a minute. And one thing is when you create or when you start the training process, you can write your custom scripts, which will be available to that container. And for this case, for this particular use case, we are going to use this particular script called train underscore deploy. And this is located under the code folder. So if you go back again, you'll see there is a folder called code. Inside that, we have that script. Now, if you go over the script, there are a few specific things which I would like to point out. Uh, Here is the max length, which we were just discussing, and this is the maximum length of the sentence that we want to consider. And we are using a tokenizer, and this will help to tokenize your sentences. And there are different tokenizers depending on different models. So we are going to use the BERT tokenizer because we are going to use BERT model for BERT pre-trained model for this particular problem. And we are using BERT base uncased. That means that the model is case insensitive. So it doesn't matter whether the sentence is of lowercase or uppercase, it doesn't matter, right? So this is, there are case sensitive models as well that you can use, but for this case, we used BERT base uncased. Okay, and if I just scroll down, then we have some data loader, a wrapper function for the train and the test, which are just like it will just fetch the data, it will check for the max length, that is 64, and it will just convert that into a tensor, and it will create that data loader. But the interesting function that we should be looking at is this, the train function. So this is exactly this actually the function where the actual training happens or the fine tuning happens. And since we are using a pre-trained model, you can see here that we declared that we are going to use BERT for sequential classification. Because we are going to use this for a classification task, and this is a pre-trained model, right? So as we discussed in Hugging Face, there are a lot of pre-trained model already there, and we are going to use that BERT based uncased model, which uses a 12-layer BERT model, which we have seen in the presentation. And we can mention that how many labels that we want to have. So since it's a classification task, we are going to have two labels, and if your task is more, if your class labels are more, you can modify that here. And these all parameters will be taken by the command line argument, and we are going to see that at later point in time when we create these estimator. And then there are a few other options that you may like to add, like output attentions, output hidden states, etc. So like output hidden state is nothing but when you keep it true, it helps us to get the embedding of all the encoder layers, right? So if you have 12 encoder layers, it will give you the hidden state of all those 12 encoder layers. For this problem, we don't care about all of that, because all we care is the representation of the CLS token, right? And then on top of that, we want to create a classifier and get the prediction, right? So that's why we kept the number of class labels as 2. Okay, so now if I scroll down, this is the training loop, which will go over the whole data set. It's a pretty straightforward thing when if you have ever worked on any computer vision problem or any deep neural network model training. We take the data set, we predict the output, and then we calculate the loss, and then we back propagate, and then we use some optimizer. So in this case, we are going to use an Adam optimizer, and we try to minimize the loss, right? And we will define how many epochs this training should run for when we start the training as a part of our hyperparameter. Okay, so at last we just have three more functions, that is model underscore fn, input underscore fn, and predict underscore fn. And I'll come back to these three functions at later point in time. But for the training part, this is what the script will do. Okay, so now if I scroll down, so this is how the training will happen now. So we are going to use an estimator object, which is available in the SageMaker SDK. And as I was telling you, if you use Keras, or if you use like TensorFlow, Scikit-learn, or whatever, you can use the respective estimator. For our case, we are going to use PyTorch, and what it does is basically it will fetch the right image of the container from the ECR, and it will create a container for you, and it will also feed the entry point script, which is nothing but the train underscore deploy.py, which we have just looked over. And we can mention what is the version of PyTorch, what is the version of Python, what is the version of PyTorch, and so on, right? And it will create a container for us, and it will get the access of the data from your S3 bucket. So this is what we are doing it here. We are creating a PyTorch estimator, and we are also mentioning how many instances we want for the training. So here the number of instances is 2. That means it's a distributed training. We want the training to happen parallelly in 2 different instances. So in this case, SageMaker will create 2 different containers of instance type P3 2x large. Right? And we can provide some hyperparameters, like we want this to run for 2 epochs, and the number of class tables is 2. And this is getting this will get feed to the script that we have written right a while back, what we have just gone through. There, if you remember, we have an option. If I just scroll up under the model function, so if you see here the number of labels, this will come from the command line argument, which will read this data, right? So based on your problem, you can set whatever it is in as a part of hyperparameter. Okay, let's go back to that function. Okay, so once we create that estimator, we are good to go for the training. And the way that you can start the training is estimator.fit. The moment you execute this, this is what happens. It will create that container for you with the right image, and it will, it will be created on the instance type that you mentioned, which is in our case P3 2x large, and it will start the training process, right? And it will have the access to all the data set that you have in the training and validation, as we are passing that location as an argument while we run this fit model, a fit function or fit method. So the output of this is quite verbose. So you can scroll down. There are a lot of good information you will get while the training is going on. But if you scroll down, you will see the test accuracy, which is roughly around 84%, which is not all that great. As we discussed, the training data set is very less, and we have not fine-tuned it. I mean, we have not used, there are a lot of hyperparameters that we could have chosen, but just for the sake of this demo, I just wanted to show you the workflow, right? So, but considering a small data set, 84% accuracy is not all that bad. And then if you just scroll down towards the end, you will see that the training seconds is 660. That means it's roughly around 10 minutes, right? So you'll be built for just 10 minutes. And this is the beauty of SageMaker. So you don't have to have EC2 machine for your training, right? Where you will be built for as long as your EC2 machine is up and running, right? So this is taken care by SageMaker, where it will just create a container for you. It will complete the training, and it will just destroy itself. Now, once this is done, we want to deploy this model, right? And we can deploy this model using a method called deploy. And as we were just discussing a while back, while deploying, you again have to mention the number of instances that you want to deployment for deploy, and the type of instance, right? So if you remember, while we started this training, we used a very powerful machine with GPU of type MLP3 2x large. Whereas for inference, we don't want that powerful machine. So we are good with, let's say, M4X large. So this is completely up to you. you can make use of any instance type that you want, and you can just run this call this method called deploy. Now, in this script, in our train and deploy script, we have three more functions: model fn, input fn, and predict fn. And what this does is basically, if you just go up, yeah, if you see this, this is the model fn function, which actually loads the saved model and returns a model object that can be used for model serving, right? And SageMaker PyTorch model server loads this model by just invoking this function, right? And that's why in this case, we are just loading this uh, pre-trained model, which is saved in our location, in our S3 location, which is, and that location is actually saved in model underscore dir, right? And similarly, we have an input fn, which actually deserialize and prepare the prediction input. In our case, our request body is first serialized to JSON, and then it is sent to our model endpoint. Therefore, in this function, what we are essentially doing is we deserialize that JSON formatted request body and then return the input as a torch.tensor object as it is required by the BERT model. Okay, and then at last we have this predict underscore fn, which basically performs that predictions and return that result back to the SageMaker. Okay, so I mean returns back to the client. So, and we are going to use that predict method after we deploy. So let's scroll down. And we are just deploying this here. And once this gets deployed, you can call that model, or you can do a inference to that deployed endpoint, right? And the way that you can do it is you can just call predictor.predict. Okay, so this is the predictor object that we have created, and it has a method called predict, and we can pass on our test sentences. So in this case, we are just creating a small list of a few test sentences. And if you can read the sentence, one, it shows that this is it's not an accident, right? It's not a disaster, although it has a word accident. But since BERT can understand the context of this word sentence, the word accident with respect to all the words in that sentence, we expect BERT to classify this as not a disaster, right? So we are just creating a small hash so that we don't get the output as 0 and 1. We expect the output to be not a disaster or a real disaster, right? So we are just simply running this predict method on all the sentences, and we are just using the argmax so that we can find out the probability of the right class, maximum probability of the right class. And if you see here, it has rightly predicted that the first sentence is not a disaster, and the second sentence, which is Frank had an severe head injury after the car accident last month, and this actually turned into a real disaster. And then there is a third sentence called just happened a terrible car crash. So this is also an accident or a disaster, right? So it has classified it rightly with a real disaster. Now, this is a very small example, but I hope you got an idea of how you can simply use SageMaker and the Hugging Face library to fine tune any model using BERT or transformer, right? So feel free to make use of this notebook. You may like to use this as a framework and build or modify the training script for your particular problem, and train it on SageMaker and deploy it and see that how you are getting the prediction. Okay, so that's all about this demo. And one last thing is, while you are playing around this, before we close off, you should clear the endpoint. Otherwise, you'll be charged for this. So you can always, run this delete endpoint method so that your prediction endpoint gets destroyed, right? So always remember to delete the SageMaker endpoint if and only, if you're not using this for any other purpose, right? Unless and until it is a production endpoint, feel free to delete that. Okay, so that's all for the demo part. And once again, please do read about the AWS and Hugging Face collaboration, because there's something new, and I really want you to go over this so that you don't have to use the transformer library separately, as we have done in our a demo. And probably I'll update this code with this new enhancement, wherein I'll try to make the code change, wherein we are not going to use the transformer module separately, but we are going to use it from SageMaker hugging face module itself, right? So feel free to have a look at the GitHub location. In future, I'll add an updated version for this so that you can compare both of that.
Thank you so much for joining this session. I hope it was useful. I'll see you soon on the other side.